Algebra 1, Common Core, Unit 9, Section 7, Arithmetic Sequences. So a couple of important notes here, but I want to mention that this is coming shortly after we spent a lot of time discussing linear and exponential functions. And we're now getting into sequences, and we're going to use terms like arithmetic and geometric sequences, but at their core, they're really just linear and exponential sequences. Let me explain. So I'm going to go to a blank slide for a moment and write down some notes. If you have some space, you can write this down. If you don't, that's okay. But again, I just want to recap the concept of linear versus exponential. Remember, linear is just like a line, and exponential is a curve. It has a constant a changing rate of change, where a linear has a constant rate of change. A linear function is something like y equals 2x, where an exponential is like y equals 2 raised to the x. And as far as the patterns go, in tables, like if we had a table like 1, 2, 3, 4 for x values, for a linear function, if it was, say, this concept, starting at, let's say, 4, and then it would go 6, 8, 10. And the pattern here is that it's a +2 pattern. And the +2 pattern is your slope. It is your constant rate of change, and that's why it'd be y equals 2x. Now, it'd be y equals 2x plus, something, some, y-intercept. We could figure that out here. Actually, I think it would probably be 2. But that's a linear function. An exponential function, again, if we make a little table to show an example of that, again, you could start at, let's start at 4 again. Times 2 is 8, times 2 is 16, times 2 is 32. So this is a times 2 pattern. And that's what makes it exponential. And that times 2 pattern, where like the pattern for linear, what you're adding constantly, that's your slope. What you're multiplying constantly in an exponential is your base of the exponential function. Now this would actually be, there'd be probably a y-intercept in front of that. Remember, your y-intercept for the linear is a constant on the end, but your y-intercept for the exponential is something, is your coefficient, something times 2 to the x. Let me get a better view there. If we actually kept these tables and went backwards, this would be 2, so the y-intercept would be here. If we did this, instead of times 2 halving, it would again be 2. So the y-intercept is in different locations in linear and exponential functions, but it's still there. It's the initial value. It's where things begin. But these patterns, we call it like a plus pattern, a multiplication pattern. They can also be thought of as a sequence. A sequence is a pattern, and it's a constantly never-ending pattern. And so this, if we could keep this going, right, and it'd be a +2 pattern, this would be a +2 sequence. 2, 4, 6, 8, 10, 12, 14, +2 sequence. And a multiplication sequence, a times 2, times 2, times 2. The next one would be 64. We could keep this going. It could be a multiplication times 2 sequence. When it comes to these linear, we call them arithmetic sequences. An arithmetic sequence is just a linear pattern with a plus pattern, a constant rate of change. And an exponential function, we call those a geometric sequence. And so we see a multiplication pattern as a geometric sequence, but really it's just an exponential function. So we're kind of changing the language here, and honestly, I don't really know why. And it kind of drives me crazy that we teach you arithmetic and geometric sequences. Why not just call them linear and exponential sequences? I mean, I kind of understand the exponential one a little bit, but anyways, just remember the connection between these two things, and it's going to make this whole sequence chapter a lot easier for you. So let me go back now to the page. And so we're just talking about arithmetic today, and the next video is just going to talk about geometric sequences, but it's helpful to remember what they are. So first of all, the vocabulary is not the only thing that changes when we start calling them sequences. It's an ordered list of terms that follows a pattern. And we use this ace of n notation. That's how you say it. It's not a of n, it's ace of n. And we use that to represent the nth term. For example, in this sequence, 3, 5, 7, 9, which maybe you could tell is a linear sequence, a +2 pattern, we would call the first term is 3, like this is the first term, second term, third term, fourth term, and the second term is 5. The notation for that would be like this. Ace of 1 is 3, meaning the first term is 3. Ace of 2 is 5, meaning the second term is 5. So if you were to see, for example, like, ace of, if I want to continue, ace of 5, the fifth term would be 11, right? First, second, third, fourth, the fifth term, the next term, if I follow the +2 pattern, would be 11. So that's what this notation represents. Sequences can be represented as explicit or recursive formulas. We'll talk more about that, and you get a lot more in depth with that in Algebra 2. And they can be, we will talk about recursive formulas. That's actually section 9.9. But for now, we'll stick with explicit. But like I said, the word explicit is not really too important for you this year. But the most common ones are arithmetic and geometric. Not all sequences are arithmetic, geometric. Not all functions are linear or exponential, but they're the most common ones we work with in this course. So if we talk specifically about arithmetic for a little while, an arithmetic sequence or linear sequence where each consecutive term has a constant difference. Constant difference is another way of saying a, plus pattern. For example, 3, 5, 7, 9 has a constant difference of 2. The reason why we use constant difference, now constant, again, remember, constant means a constant rate of change. That's, again, that connection between linear is its constant rate of change. The reason we're using difference is you can think of this as a +2, +2, +2, but you could also think any term is, 2 more than the previous. That's a difference of 2. Like the difference between 9 and 7 is 2. Difference is a form of subtraction. And so you could kind of just see that common difference a lot of times. Like you could tell it's a +2, +2, +2 pattern. But if you can't tell, and we use a D to represent difference, but again, really it's just slope. Sometimes we use M. In sequences, we call it D. But it's any term minus the previous term. So like 9 minus 7 is 2. 7 minus 5 is 2. 5 minus 3 is 2. Pick any term in the sequence minus the one before it, and you get the constant difference. You get the slope of the function. Now, this is only for arithmetic sequences, though. But that's what we're talking about in this video. So for each sequence below, state if it's arithmetic, and if it is, what's the constant difference? What is the slope? So 3, 8, 13, 18, is this a linear pattern? Is it an arithmetic pattern? The easiest thing to do is kind of check it. So how would I go from 3 to 8 with addition? It would be like +5. Is that also true for the rest of it? Does that +5 pattern hold true? And in this case, the answer is yes. The +5, 3 plus 5 is 8, and 8 plus 5 is 13, and 13 plus 5 is 18. So yes. So yes, this is arithmetic, and the constant difference, D, equals 5. How about 2, 4, 8, 16? Well, 2 plus 2 is 4, but it's not a +2 to get to 8, so no, that is not arithmetic. It's actually geometric, exponential. We'll talk about that in the next video. How do I get from 5 to -1? Well, 5 plus, the number's going down. So you could think of it as one of two ways. I could think of it as minus a number or plus a negative, right? Plus -4. And does that also work from 1 to -3, -4, or plus -4? Yes, this one also works. And so your constant difference is a -4. So you could have linear sequences with, remember we could have negative sloped lines or positive sloped lines. The same thing here. We have a formula, an explicit formula for the nth term of an arithmetic sequence. Basically, if I have a sequence like this and I want to know what's the 20th term, I don't have to keep the pattern going until I get to 20. I could jump right to 20 by using this formula. And the formula, a sub n, equals a1 plus n minus 1 times d. It's pretty much another version of y equals mx plus b. It can get a little confusing when you constantly try to compare the two, but that's really what's happening. Remember your D is basically your M, your a sub 1 is like your y-intercept, but it's kind of the same thing. So determine the 15th term of the arithmetic sequence. Here's an example here. Remember, a sub 1 means first term. So the first term in the sequence is 5. n minus 1 means if I want the 15th term, I plug in the number 14. So where's my work here? So our first term is 5. 15 minus 1 for n minus 1, because if I'm doing the 15th term, it means n is 15. Like I want a sub 15. So 5 plus 15 minus 1 times the constant difference is 4, because you see this pattern has a plus 4 pattern. And follow that through, we get a sub 15 is 61. Let me show you one. I think it's easier to understand it when I do it from scratch. So the formula, a sub n equals a sub 1 plus n minus 1 times d. Just give me 1 second. I just wanted to check real quick your reference sheet. I'm pretty sure, yes, this formula is on the Regents reference sheet that you get on the Regents exam, and your teachers will give it to you in class. So it's not a formula you need to memorize, although you probably end up will. So we want the 7th term. That means we're looking for a sub 7. We start with a sub 1, the first term, 2, plus, now n, because we're finding the 7th term, n is 7. Right? So your 2 is your a sub 1. Your 7 is because we're doing the 7th term. And that's 7 minus 1 in parentheses, times d. Now, d is the pattern. What's the pattern here? Numbers are going up, so it's going to be a plus. From 2 to 6 is 4. 6 to 10 plus 4. 10 to 14 is plus 4. And just work this math out a little bit. So 7 minus 1 is 6. And 6 times 4 is 24. And 2 plus 24 is 26. So the 7th term of the sequence is 26. And if I keep doing a plus 4, plus 4, plus 4 till the 7th term, I would get 26. Okay, the very last thing is, how could I create a formula to represent, like this is for the 7th term, but what if I want a generic formula? Like this is the formula, but I want one specific for this. Basically, leave n as n and just substitute in a sub 1 and d, like this. So a sub n equals, now in this case, a sub 1 is 2 plus n minus 1, I'm going to leave as n minus 1, but d, I'm going to change to 4. And what we could do here is distribute this. So it's 2 plus 4n minus 4. And I can combine like terms with this 2 and this minus 4 to get a final formula of 4n minus 2. Now, doesn't that remind you of y equals mx plus b? It certainly does for me. Your slope is 4, your y-intercept is 2. That is it. That's why this arithmetic sequence is nothing more than a linear sequence. All right, and this is, creating a formula that, could be used to represent the entire sequence. This is just using it for the 7th term. I could use it for any term that I want to find. All right, so that is arithmetic sequences, which is, again, just another way of thinking about linear functions, and we will talk about the exponential or geometric ones in the next video, 9-8. See ya.